because it's such a broad field with so many topics to be addressed that you always have the feeling that you don't know enough in this field. Maybe it's always the same for research, but I started my career working on cumulative total ionizing Gauss effects on several types of devices. And then after 10 years ago, we tried to find a way to put some payloads with radiation effects experiments in flight. And we had this wonderful collaboration with Victoria's team. Maybe you've met Vasily, Andre, and others. And it was a very, very fruitful collaboration. And we were very sorry that the rocket didn't do a proper job to put the satellite in orbit. However, we flew the experiment on one of our CubeSats, and it's still working, it's still up there, and we're still getting results that I will show you today. So the topic of this lecture will be radiation effects in the moon environment, which is very, very broad because there are so many things to address, ranging from radiation, the interaction between particle and matter, the moon environment, space environment, and then the effects on biology and also on electronics. If I'm correct, the general background of the attendance is more like mechanical engineer or space engineering, not too much into electrical engineer. So I will not spend too much time and will not go too far into semiconductor physics and electronics, but I will just give you a broad overview. It was a difficult lecture because in such a small amount of time, being able to do something that encompasses, gives you a flavor of what radiation effects are and how to deal with it is quite complicated without doing some National Geographic style survey of the radiation effects. So, well, let's try and see what we have. So I'm with the University Space Center of Montpellier, and after our first satellite launch, we decided to create this facility, and it's been growing rapidly. And now we are 15 staff, and we get 30 interns. We have a lot of facilities. We can do a full mission from concurrence design to TVAC and vibration and everything. But our strong point is still radiation effect because our group has been working in this for a lot of years, many, many years. I would just like to mention that one of main activity is to have interns working on our satellite missions. So if some of you are interested in applying for an internship, just go to our website. Click on it. We are located on the south coast of Montpellier, near the Mediterranean Sea. It's definitely not a bad place to be, and the Russian students who came, I think, had a really nice time in Montpellier. So, as I said, radiation is a very broad topic. It encompasses a lot of disciplines like nuclear physics, semiconductor physics, electrical engineering. You could go to circuit effects, software systems, biology, legal aspects. They're getting more and more important in this field. And of course, it's impossible to address all the aspects in such a short time. In addition, if you focus on the electrical engineering part, just to give you an example, the radiation effects are family dependent. Means that if you talk about MOSFETs or bipolar junction transistor, you get a completely different effect. They are part dependent, they are technology dependent, manufacturer dependent, and even lot to lot dependent. It means that if you buy two devices from two different manufacturers, from or the same device from the same manufacturers, but from two different date codes, lots, then the effect will be different. One can be very good, the other can be really bad. So in this lecture, what I would like you to understand is don't expect me to give you universal recipes to address radiation effects. The rationale is to give you the basic rules, and then you can use your brain in your situation, facing your environment, facing your design, to address the radiation effects. And I would also like to avoid you to do the big mistakes that some people sometimes do, especially with shielding, because shielding should be the solution. You put some shielding in between the source and the target of radiation. And actually what you do most of the time is that you make things worse. So shielding is not always the solution. I will focus
Mr. Laura, I'm sorry for interrupting. It seems like you have sharing with us both of your screens. Could you please go through the...
Okay, maybe this is better?
Slightly, yes.
I'm sorry, I don't know how it works. It should be...
That's better? Perfect, yes.
Yeah. Okay. Okay, so I've given some bibliography at the end of the slides, but there's, for non-specialists, there's a must read, which is this document in which you will find another complete overview of the radiation effects. It's quite good, it's quite well done, and it's quite understandable for most scientific people. One thing is certain is that the radiation represents a huge hazard for space mission. And this is for two different reasons. The first reason is biological, because the radiation may kill the astronauts very quickly. And the second point is by material and equipments, because if you alter the good functioning of your equipment, then you may have catastrophic failures. And this happens quite often. Space environment is not something that is always the same. It's very versatile. You know that the sun, for instance, follows a cycle, an 11-year cycle, and it's very difficult to predict what's going on. For instance, when we launched Robusta 1B, one of our first satellites, we were in the minimum of solar activity, so nothing should have happened. However, after a couple of months in space, we have recorded a tremendous solar event, and we had a lot of TID deposited in our sensors, which was actually what we wanted. But had astronauts been in the outer space at this moment, they would have probably died. So there are some dangers that can be found on the journey that I will list in a moment. And if you want to go to the moon, you have to make sure that you avoid as much as possible those dangers. And to do that, you have to pick the right trajectory to get there. Shielding, yes, it's an option, and you should make use of shielding, but you should do it very carefully, because as I said earlier, shielding could make things far worse than it is. So there are some effects on the crew members, on the electronic, and we have to try to mitigate them as much as possible. And this is what we're going to look for. So the outline of this talk, first I will tell you about the radiation basic quantities, because it's like talking about electrical engineering. If you don't know what is a volt and an ampere, you don't understand what you're talking about. Then we go through the radiation environment on the way and at the moon. It cannot be dissociated, because in a mission you may have early failure just after the taking off. So it's something that has to be taken into account. Then we'll go to the radiation effects, biological, TID, which is total ionizing dose, and single event effects, the two big families of effects that you should get on the spacecraft. Then we will summarize, and if we still have some time, we can go for Q&A. Okay, as you may know, radiation was discovered by, or at least radioactivity was discovered by Henri Becquerel and Pierre-Marie Curie. And they gave their name to a famous unit, which is the Becquerel. The Becquerel represents one disintegration of an atom per second, so the emission of one particle. It's a very small number, so we prefer to use the Curie, which is much bigger and suits better for most applications. On the ground, when the particle is emitted, no matter where it comes from, it is often attenuated because it will encounter a layer of matter, no matter if it's air or if it's the ground, if it's a shield of whatever, or your skin. But in space, all the particles coming from the sun, from the supernovae in space, from wherever, will travel through the voids. And especially if they are accelerated to very high velocity, they will travel forever until they reach some elements that will stop them. So in this outer space, we talk about the flux, which is the number of particles that you get per centimeter square and per second. And then if you integrate this number on a long period of time, you get the fluence. So at the end of the mission, you can say that an equipment has received a fluence of 10 to the 16 particle, for instance, or a solar cell has received this fluence of particle. Speaking about the solar wind, it's often the density is often used, which is the number of particles per centimeter, per cubic centimeter. For instance, you have 10 to the 10 proton per cubic centimeter in the solar wind during a period of time. So these particles travel, and then suddenly they hit the matter, and something happens. This happens in a different way. If it's a charged particle, it will interact with other charged particles. If it's not, the particle is not charged, it's a statistic interaction with the nucleus, for instance, if it's a neutron. And in this case, you may have nuclear reactions of all sorts. So you can see the difference between statistical interaction. Do I hit the nucleus or shall I not hit the nucleus? And on the other hand, it's a determinist interaction between charged particle. You are sure that charged positive proton, for instance, will draw a negative electron. This will arrive for sure. And then when you do that, you deposit energy, the particle deposits energy, and this energy is quantified, and it's given by LET, linear energy transfer. I will explain a little bit later. The dose, which everybody has heard about, and the speed at which the dose is deposited, which is the dose rate, and expressed in gray per second. So the unit of dose is in the SI system, it's a gray, and the dose rate gray per second. But that's not enough, because you have many types of particle encountering different type of targets and causing different effects. So the dose doesn't describe well the effect. For the same dose, different particles will have different effects. It's getting complicated. So sometimes, and especially when you're talking about biological effects, you need to have a quality factor that describes how bad the particle is. And I will explain that a little bit later. When you talk about ionizing radiation, I'm leaving aside the non-ionizing radiation, like the visible light, for instance, only talking about ionizing radiation. Ionizing radiation means that you are going to strip your atoms from the electrons. And if the electrons are free, they can participate in the conduction, for instance, of a material. So to do that, as I was starting to explain earlier, you have two ways to deposit energy. The first way is deterministic. It's a charged particle going through matter, interacting with the electrons or the nucleus through Coulombic interaction. and you know exactly and for sure how much energy will be deposited when the particle stops, and you know exactly where the particle will stop. This is called directly ionizing particles. On the other hand, you have some particles that don't have any charge. So they have to interact through a different mechanism. So as I said earlier, this mechanism should be just pounding into an atom and a nucleus and making it blow out, which is causing nuclear reactions. It's different for photons, for instance, because they have to interact between the famous Compton or photoelectric effect. I'm not going to talk about the photons today. I don't have time, and since we don't have photons in the environment or they are negligible, I will not elaborate on the photons. But neutrons, we'll see that they're quite important in the moon environment. So basically, an alpha particle will be stopped by a sheet of paper. Beta particle is stopped by a sheet of aluminum. And then if you have gamma or neutrons, you can put as much material as you want, as thick as you want. Some of them will always go through because they just miss their target. So to give you the basic definition, the unit is 1 gray for the dose. 1 gray is 1 joule deposited for 1 kilogram per kilogram of matter. Just to give you an example, 1 calorie elevates the temperature of 1 kilogram of water by 1 millidegree. It means that if you deposit 1 gray, you will elevate the temperature of your tissue, body tissue, by roughly 1 millidegree. It means that it gives no warning. If you are irradiated, you just don't feel anything. And this is what is really, really nasty with radiation. It makes it a very silent killer. So the lethal dose is 4 gray, which means that if your full body, your whole body receives 4 gray, you're dead. Or at least 50% of the population irradiated with full body will die. That's the definition, the official definition. No hit, no warning, but 50% of casualty. In the radiation community, we still use an old unit, which is the rad. And since it's a small amount of energy for electrical devices, we often use kilorad, which is equivalent to 10 gray. So if I speak about kilorad, don't be surprised, it means 10 gray. Just a small note, but it's quite important. An energy is an energy. It's just some joules. Mass is expressed in terms of kilogram, and we don't care if it's fevers, lead, or water, which means that the dose, which is the ratio between the energy and the mass, does not depend on the material. But the amount of radiation needed to deposit 1 gray is different from one material to another. So don't be surprised in the literature if you read some rad-Si or rad-SiO2. It doesn't mean that the dose depends on the material. It only means that the source was calibrated to deposit 1 rad in silicon or to deposit 1 rad in SiO2, and this is very important when it comes to radiation testing. So to give you just a few figures, I found this very interesting example of the dose received by the astronauts during their moonwalk at the surface of the moon. So basically, it was a few days, between a few hours and a few days. And the amount of radiation received was 1.1 rad at the most. So keep that in mind. I will come back on that a little bit later when we talk about the effects. And we'll compare that to the dose that you guys receive every day or every year at the surface of the Earth. So as I said earlier, we have a charged particle that is passing through the matter. And when it's passing through the matter, it's obvious that, for instance, an alpha particle, which embeds two charged protons, will draw an electron. And drawing this electron, if it draws enough on the electron, it will strip the electron from the atom, which creates the ionization. So now let's have a look at this particle. If it's an alpha particle or a heavy ion, for instance, going through the matter here, you see that it will not be deviated because it's a heavy particle with a strong momentum. It still goes through the matter like this. And then the ionization occurs all along the track, okay? On the other hand, if you have a light particle like an electron entering the matter, it will interact with both the atom, the nucleus, and with the other electrons, and then it will bounce back and forth and even come back, which is called backscattering. So it's a completely broken line like this. And then we have a depth of penetration like this in the material, which is not equal to the length of the path followed by the electron. So what you can already see from those two figures is that two different particles have a completely different effect, because on one side you have one particle going through on a straight line, on the other one you are scattering the energy all around the surface or the volume that you are considering. So the next question is, this particle that is going through the matter is going to lose energy. I make a difference between losing energy and depositing energy. We'll see that later. Keep it in mind. So this definition of the stopping power applies to the incident particle. It's the ability for the particle to stop or to lose energy on the way. It's defined by d over dl, where dl is the length, incremental length. So it's the energy lost by the particle per unit of length. And if you want to make it independent from the target material, all you need to do is to divide by the density of the target material. And then you have a definition that only depends on the number of charge and the mass of the incident particle, okay? So you can compare different particles, even if they enter different materials with that. So remember, stopping power, from the point of view of the particle is losing energy. Why am I making such a difference is because the energy may be lost somewhere, but deposited much further. And you know this because when you take an X-ray, the energy is lost in the cathode of the X-ray machine, but it's transported by X-rays through your body to end up in the plate, the photographic plate. So the energy is lost somewhere, but deposited somewhere else. So what we are really interested in this lecture is the moon. So let's have a look at the density of the moon regolith. And the moon regolith, measured by the several missions who landed, is given in this table. And as we can see, it's a lot of oxides, basically. So it's not a surprise that we can find a lot of oxygen. And basically, the main composition of the regolith is the silicon dioxide. And the density here is something between 135 and 185. It's lower than the density of solid silicon dioxide, but still it's silicon dioxide. Just to compare, usually the shielding thickness are given in aluminum equivalence density, shielding thickness, and the density of the aluminum is 2.7 grams per cubic centimeter. So we also have other materials. Some are heavier, some are much lighter, like calcium, for instance, or magnesium. So all in all, the density of silicon dioxide is a good example to run simulations. So I have used software called P-star, A-star, and E-star, describing the stopping power of particles, of protons, alpha particles, and electrons. And I obtained those curves. So basically, I could spend a full lecture on those three curves because there's a lot to say about it. But what I would like to stress on these curves is that you should read them from right-hand side to left-hand side. It's just like if a particle was coming this way. So it arrives in the material with a lot of energy, and then it's losing energy on the way until it stops, okay? And what is plotted here is the energy lost by the particle as a function of the incident kinetic energy. And what you see, which should be a surprise, is that the energy deposited actually increases as the particle slows down. It shouldn't be such a surprise because if you think, if you had a very energetic, a very fast particle going through the matter, it will, for instance, a particle with a velocity close to the light velocity, it would just go through the matter without interacting at all. But when the particle is slowing, it has much more time to interact with the electron. And then the momentum transferred to the electrons or to the nucleus in the material, to the lattice, will increase because the momentum transfer depends on the interaction time. Duration. So a slow particle has more time to interact. And then in the end, it's going down a little bit because the alpha particle may capture electrons. It's become very slow, very low energy. So it will capture electron, deionize, and then deposit less and less energy. Alpha particles are heavy. So for the same kinetic energy, the mass is higher, okay? So don't be surprised to see the same phenomenon happen for protons, but for higher energy, since the mass of the proton is much lower than the mass of the alpha particle. And then once again, this region of the curve can be found here. And you see that your proton slows down and deposits more and more energy until it stops. And regarding the electron, which are very light, you can see that this region in which the stopping power increases here is also here. But then you have for the higher energy, you have this slope here where the interaction becomes very strong again. And this is due to an additional mechanism, which is called Bremsstrahlung, which is usually used to produce the X-ray. So it means that the energy is converted into X-ray and not transferred to the electrons of the material in this field. So basically remember that the particle slows down, and the more it slows, the more energy it loses on the way. Which means that if you have electrons and protons and you put some shielding, for instance, you have 100 MeV protons, incident protons, and you put a thickness of shielding, after your shielding, you may be at the maximum of energy deposition. So your target will receive actually much more dose than without the shield. And I'm not talking about the X-rays and the secondary particles that you should get. So once again, shielding is something that should be used very carefully. So the next question is, those particles, they slow down, they pass through the matter, but when do they stop? How much shield should I put to stop them? So if we look at the alpha particles first, right here, you can see that typically 10 MeV, 100 MeV alpha particles will be stopped sorry, the curves here are expressed in terms of mass stopping power, which means that it's been divided by the density. So if you have a rough estimate of the length it actually gives, you just have to divide by a factor of 2, because the in the regolith, in the aluminum or in the silicon dioxide, it's roughly, the density is around 2. So you see that the alpha particle will stop within a few microns. So basically alpha particles will be stopped by a sheet of paper. But 10 MeV protons here, they will need a few centimeters to stop. And 100 MeV proton will need a few centimeters to stop. And the electrons, they can go much further if they have enough energy, because, but once again, they move into a broken line. So you can use those software A star, E star, and P star to calculate the thickness of shielding that you need to stop the particles, but make sure you put enough thickness of material between your targets and your source, because if the proton goes through, they will be worse than they were before. Okay, so beware of that. Okay, in the stopping power, I looked at the energy lost by the particle. So now you have almost the same quantity, which is the linear energy transfer, but this time we're considering the energy deposited inside the material and not lost by the particle. As I said, the energy can be lost somewhere but deposited somewhere else, which makes things a little bit different. And this is because you may have, for instance, electrons transferred into X-rays, or alpha particles creating, or protons creating secondary particles that will transport the energy somewhere else. Let's have a quick look at the neutrons, because there are some neutrons on the moon. We'll see why. And the thing that we want to avoid at all costs when doing some shielding is to have fission reactions, because you know how bad this can be. Your neutron is blowing up, eating a nucleus, then the nucleus gets spallation, or you get a nuclear reaction, then you have got heavy fragments going their way, and then you have some more neutrons creating more and more nuclear reactions. This is quite bad, because if this happens, for instance, with a neutron hitting a silicon atom in an electrical part, then it will create the nuclear reaction and the fragments inside the components. For instance, it can happen inside an SRAM or a memory, a DRAM. And then you will have those heavy fragments depositing a huge amount of energy on their way. And they can make a lot of memory cells shifts. So you have many zeros becoming ones and many ones becoming zero. This is a big problem. Then you have also another capture, where the neutron may be captured, and then after a while the atom the nucleus becomes radioactive. Then you get a reaction where your neutron is explodes with a lot of fragments and protons and neutron and alpha particles. So this is also not an option for shielding. It's getting better if you put a reaction between neutrons and neutrons, or neutron and a light material. And in this case, you may have inelastic or elastic diffusion. In the case of the inelastic diffusion, you have the emission of a gamma ray. And in the case of the elastic diffusion, which is the base case, the target neutron or target nucleus and the neutron will share the energy. And if you manage to have a neutron hitting a light nucleus like hydrogen, for instance, then it's almost the same mass, and then the energy is divided by 2. The momentum is divided by 2, the energy is divided by 2. So you find yourself with 2 neutrons, or one neutron and one we call hydrogen, but they both have less energy than they used to have. So after a few interactions like this, you degrade your energy and your neutron finally gets what we call thermalized. So they're slow neutrons and they're not as bad as they used to be. So to mitigate neutrons, elastic diffusion should be favored. So hydrogenous material should be preferred. Don't use a big, heavy nucleus because it will be affected by the neutron to create fission, or the neutron will just bounce back with the same energy. But if you have two nucleus with the same, two particles with the same mass, they will share the energy after the shock, and then you will degrade the energy. So you can make use of your water tank, your fuel tank to provide a good protection. So I'll put all the tank around you, around the section of the spacecraft or the facility that you want to protect. It's not easy to calculate. It's not something that you can calculate on your table with a pen and a sheet of paper. So you can use Monte Carlo calculation codes to evaluate the neutron-driven dose. Giant 4, for instance, can be used for this thing. It's not easy to use. You have to be a specialist to use it. So I think I'm done with this first section. We have a nice overview. Let's keep in mind this increasing energy deposition when the particle slows down, because it's very important. And let's also keep in mind that to stop neutron, you have to use hydrogen in water or in the fuel. So now that we have a background, we can go to our topic, which is the radiation on the journey to the moon. So radiation should really be taken into account at all phases of the mission. Typical trajectories, you'll see, have a lot to do with this. And if they go through something like 51 degrees inclination and 40 degrees north altitude, and the peak altitude 200 kilometers, this has been carefully chosen to avoid radiation effects. It's not only a question of dynamics. You should take into account the radiation effect during both launch and ascent. Maybe you're not aware of that, but it's important. You should take radiation effects into account into LEO phase as well. Into, of course, the deep space, outer space segments in orbit around the moon, and of course at the surface, and also during re-entry and landing. So you would say radiation effect is not such a big issue for takeoff. Let me show you something. When you're taking off, you have to go through the first 20 kilometers of the atmosphere. And in this region, the cosmic rays from the sun or from outer space interact with the atoms and produce cascades of particles. And some of those particles reach the ground. And if you fly around 10 to 12 kilometers, what you find is a lot and a lot of neutrons. And those neutrons affect the aircrafts. They affect the crew members of the aircrafts, and they may also affect the electronics on board, creating errors, and those errors could be deadly. So do not neglect in the system the radiation effects on the launcher and the capsule during this phase. Very important. Please also keep in mind that the same condition also applied during the re-entry. Within the same altitude and limit. To illustrate that, I would like to show you this very nice picture. It's a picture that I took on a beach in South Africa 2 years ago. If this picture is really special, it's not because of the white sand or the blue water. It's because of this. Can you see the mouse? It's because of this structure right here. And guess what it is? tell me, what is the probability for a neutron to interact with my CMOS imager in my smartphone exactly at the moment when I was taking the picture? And most important, what is the probability for this to happen in the mobile phone of a guy who's a specialist of radiation effects and who can tell this is radiation effect in my CMOS imager? I swear this is not Photoshop. What you get here is an incoming neutron that hits an atom of silicon into my CMOS imager, creating recoil fragments, nuclear reactions, and the nuclear reaction have deposited the energy, interacting again with creating other fragments, and so on to get this cascade. And this cascade is affecting thousands of pixels. So if those pixels had been memory cells, they would have created such a huge error in the system that the system would have not recovered. And that was on the ground. I'm not talking about that at the altitude of aircrafts or at 20 kilometers with a launcher, okay? So please don't forget to take into account the radiation effect at this altitude. So let's imagine now that we have had a liftoff. We have reached the low orbit zone. We have orbited a few times around, and then we want to leave. And then we find a very big danger on the way. And this danger is called the Van Allen belts. You may have all heard about the Van Allen belts, and so I will briefly just remind you what they are. The Earth has a very nice magnetic field surrounding us. And this magnetic field is fantastic because it's screening us from all the cosmic rays and solar events. But since there are magnetic fields, the particles coming from the sun, the solar winds, and they just get trapped into these magnetic fields, bouncing back and forth from the poles and creating what is called the Van Allen belts that were discovered in the 50s. And we have several zones, and the most dangerous one is the inner radiation belt, because it's quite close to the Earth. It ranges from 1,000 to 6,000 kilometers. So in this area, and here the amount of radiation here is simply tremendous. Nobody wants to put a satellite in there because it will not last very long. And I'm not talking about the astronaut. The only people who want to send satellites there is us at the University Space Center. We are going to launch 2 kamikaze satellites in this area at the end of the year, equipped with a lot of radiation detector and radiation experiments. It will be launched with the maiden flight of Vega C. And then we will investigate for maybe a few weeks or a couple of months, maybe, the radiation effect in this zone. And we expect the satellites, although they are really, really rad hard, we expect them to die within 2 months in this area. So there's also another radiation belt. It's a little bit below the geostationary orbit and MEO orbit. And what you want when you want to launch astronauts or a spacecraft to the moon, you want to avoid this area right here. So this is why they choose this trajectory that went around the inner radiation belt. It was not the optimum for in terms of ballistics and astrodynamics, but there was no other way than flying this way. So that for Apollo 11, for instance, the traversy of the radiation belt took 90 minutes, and they tried to avoid this region as much as possible. So now we have escaped the radiation field, the protection field around the Earth. So basically we are naked. There's nothing left to protect us around the radiation, no more shielding. So then we are exposed to first the solar wind, solar particle event and cosmic ray, cosmic galactic rays. And this is true for the outer space, but also for the moon surface, which is directly exposed to this kind of particles. So let's first consider the solar wind. The solar wind usually is a plasma of electrons and protons with a speed of around 400 kilometers per second, which is not much, by the way. Sometimes it's accelerated by coronal holes and can reach a speed of, very briefly, a speed of 800 kilometers per second. It's also linked to the geomagnetic perturbation. I'm just mentioning it so you've heard about it. And geomagnetic perturbation are quantified using an index which is called Kp. And sometimes in the solar wind, you see proton bursts, which are an enforcement of the proton density with an increase of the velocity. And those recently have caused a lot of failures on satellites. They have killed a few CubeSats. And you can correlate the sudden death of CubeSats with the proton events in the solar wind. It's something really clear. You can do that very easily by checking at the same time SatMogs and Space Weather Live, the Space Weather Monitoring website. Solar particle events, they cover a broad range of events. Most famous are the coronal mass ejection and the solar flares. Basically, in both cases, it's a lot of particles accelerated. And if you're on the way of this, on this event, you're in a very bad shape. Fortunately, the solar cycle of 11 years make sure that if you are in this region where the sun activity is very low, very quiet, then you have a good chance to escape this. As I said, you may still have unexpected solar flares or CMEs in these regions that happened in 2017. Well, the chances of surviving are better in this period of the solar cycle. Well, the most energetic particle will reach us in less than 1 day, which means that if it takes 4 days to travel to the moon, and this happens in the middle of the journey, then you're in really bad shape because you will be you can just hope that the CME or the solar flare will go in another direction and will not come toward the heat. Toward the Earth. So it's easy to visualize the effect of such a solar flare if you look at an imager. So this is a coronagraph looking at the sun, so you can see the corona. It's very clear, very nice. You can see the stars all around. And then suddenly you have a solar flare, and the light particles traveling faster arrive, and they start hitting the imager. So you see all the dots, and then the heavier particles arrive, and it's even worse. And some of those pixels will never recover, and they will stay white. At system level, I would just let you imagine what it would do if this was a star tracker. Star trackers, what they do is that they try to retrieve your position, your attitude, by looking at the stars. Where are the stars? You see, no more stars, no more attitude control, and you're lost in space again. And it's very difficult to recover from that, or you will have to use a lot of fuel and your propulsion system to recover your attitude, a lot of energy. So just to summarize those particle events, you may have protons from 20 to 80 MeV, so they're very difficult to shield. You need a thickness of aluminum of 2-3 centimeters to shield them. They will arrive within 10 hours if they are really energetic. And if we look at these curves, we have the flux of particles recorded during the most famous solar flares. And there's one that is especially interesting, which is, I guess, the most important solar flare ever recorded, which happened in 72 here. And you see the increase compared to the basis of the usual cosmic rays that you get. You see this huge increase in the flux. And why is this especially important? Because it occurred in between the Apollo 16 and Apollo 17 missions. And it would have been lethal in 10 hours for the astronauts. Had there been in flights at their time in the outer space, they would have received the lethal dose in 10 hours. So you just understand that sometimes you have to take a risk because you never know when this is going to happen. It's just going to happen sometime. Just cross your fingers and make sure you're not there when it happens. And the last source of particles is the cosmic and galactic rays. And the definition is, it's when you have a supernova that blows up somewhere. It sends very high energy particles all through the universe. And those are so energetic that it's not possible to stop them. And you even have very heavy nuclei with huge, tremendous energy. If you look at that, you can see that here you have the fluence of particle as a function of versus the energy per nucleon. So if you look in red, you've got iron ions here. You multiply by 30, 40 for the iron here, and you see the immense, tremendous energy carried by those ions. So don't even try to stop them, it's just not possible. So to summarize this environment section, if you look at the flux density of particle as a function of the energy, on the right-hand side, you've got the cosmic and galactic rays, very high energetic, but fortunately, there are not too many of them. On the other side, the solar wind protons, they're not so energetic, but there are a lot. And in between, you have those scary solar storms here with the variability with time here, and the trapped electron, the belts, and so on. So it's this full environment that you should consider, because here it's low probability but very high risk. Here it's low risk but high probability. So it's kind of a difficult environment to assess in terms of risk analysis. And now let's have a look at the environment of the moon itself. Once you have landed and you want to take a moonwalk, what will you receive? As I said earlier, the moon doesn't have a magnetic field. So we don't have a shield, a natural shielding of the moon. So every single particles coming from the sun or from the supernovae will hit the surface. And if they hit the surface, they will create nuclear reactions. And who says nuclear reactions also says neutrons. And those neutrons, as I said, are very difficult to stop. So they will penetrate very deeply. And so you may have, especially with secondaries and cosmic and galactic rays, you may have interaction with the regolith down to 5 meters below the surface. So if you want to use the regolith to shield yourself, you have to dig, but you have to dig very deep. Don't stay in the surface, otherwise you will get a lot of neutrons for secondary interactions. Basically, that's it. So just to summarize, I have found this very nice tables with the types of particles in the environment, just to remind you, the solar wind, the cosmic rays, the galactic and cosmic rays. And you see that, for instance, protons and alpha cosmic rays, they interact at meters. So you need to dig very, very deep. And even the solar the solar cosmic rays, it's a question of a few centimeters or tens of centimeters to cover. Okay, so now we've seen what are the basic quantities. We are more familiar with the environment. We are facing protons, we are facing electrons, galactic rays, heavy ions, and we are also facing neutrons, okay? So it's a very rich radiative environment. And now when we are exposed to this environment, we take a risk. So what kind of risk do we take? What is the risk for us, the crew, and what is the risk for our equipment or our facility? So it's not so much the topic here, but it's important for me to make you understand how the radiation damage the biologic systems. You remember what I said earlier, 1 gray is 1 joule and the lethal dose is 4 gray. The elevation, temperature elevation caused by 1 calorie is 1 millidegree, so no heat. No heat means no warning. Then it means that the damage is caused differently. You will not boil, okay? And still you're dead. So how does it work? If you correctly remember, from the physics point of view, what happens is ionization. So the particle going through the matter will create an ionization of the atoms constituting your body. And then you have 2 types of effects. The first effect is an immediate effect due to the chemical transformation that may be caused by this energy deposition. And this will cause an immediate destruction of the cells. But most of time for low doses, what happens is that those particles will break the DNA helix. And if you break the DNA helix in 2 pieces, then we are protected against that by something that is called SOS functions, which reconstitutes the DNA. But if you deposit a lot of energy because you have a very high LET on your particle or you cause great damage, then you will break your helix in a few fragments. Then they try to reconstitute, but there will be mistakes, errors, and those errors will definitely create cancers. And this is why we have delayed effects that will affect your body. So once again, the notion of dose does not describe well the biologic effects. Because if you get irradiated with cobalt-60 gamma rays or with neutrons or alpha particles, the damage will be different. So the biologists have introduced what they called factor to take into account, for instance, the fact that for the same dose, alpha particle will cause 20 times more damage than gamma rays or electrons. This is called the quality factor. So it can be easily evaluated by taking bacteria in Petri boxes, and then you irradiate them with depositing the same dose but different types of particle, and you just evaluate the mortality of how many bacteria die for each type of particle. And then this is how you can find that, for instance, for alpha or neutrons, the number of dead particles is much higher than for gamma rays or electrons. So taking this into account, then you transform your gray, which is 1 joule per kilogram, into sievert. And the sievert is just 1 gray multiplied by the relevant quality factor for the particle that you are considering. And if you're talking in terms of rad, then the equivalent would be the REM, which is 1 rad multiplied by the quality factor. It's a bit much more complex than that, but I'm doing my best to explain with the time I have. So if you are interested in that, you can go to the NCRP reports and you will find a much precise definition of this. So it also depends on the organs that are impacted by the radiation. And this is it's a recommendation for the exposure. So for instance, for a mission like this, based on a 3% risk of excess cancer mortality, which is the criteria used to for the missions, then you tolerate 1 sievert at the high level, 1.5 sievert at the skin level, but only 0.5 sievert square at blood-forming organs, because they produce the blood, and if the cells that are produced are damaged by the radiation, they will replicate, and then you get a bad cancer. So just to give you a comparison, I would like to show you this those quantities. I'm just taking a few ones. The cosmic rays at sea level will give you a dose every year of 0.024 rems. So basically we are 0.0 something at ground level. If we come back to the dose received by the astronauts, they're expressed in rad, but we can just assume that its rem is equivalent to a rad to have an order of magnitude. And you can tell that they're in the range of one rad. So basically it's the order of magnitude is 100 times higher than what you get on the surface of the Earth per year. Okay, so within a few hours, they got as much radiation as you would get on the ground in 100 years. If you're interested, I'm not going to spend too much time on that, but you also have here the dose deposited into the regolith as a function of the depth into the regolith. And you can see, you remember, if you want to transform this unit into centimeter, then you divide by 2. And you see that you've still got a significant dose deposited by neutrons after 3 meters, at 3 meter depth below the surface of the moon. Okay, so I know that most of you are not electrical engineers, so I try to make things as clear as possible to explain the radiation effects, and this will be the last section of my talk. So first, I would like to tell you that there are 2 different types of radiation effects. The first type is what is called ionizing radiation, TID. It's a cumulative effect, but you also have what is called displacement damage dose, total non-ionizing dose. And this is due to the fact that your particle may not only interact with the electrons, but may also interact with the nucleus. They're just pushing the nucleus away as they cross, for the same reason, because they are electrically charged. So plus and plus just you have a repulsion between plus and plus, positive and positive charges. Single events, they are caused by usually a heavy particle. So if you correctly remember, heavy particles with great ionization along a track. And if this track is in the active region of a device, you may have destructive or non-destructive single event. So in this case, it's a lot of damage caused slowly in time. In the case of a single event, it may occur at the first instant of the mission. If the wrong particle goes at the wrong place, at the first instant of the mission, you can get a catastrophic failure. It's we know that this particle will create ionization along the track, and now what we need to do is to quantify this ionization. So all we need to do is to know the amount of energy it takes to create one electron-hole pair. Okay, if you know this, the average value is fine. You can calculate how many electron-hole pairs will be created by an ion or by a proton passing through the matter. And why is this important? It's important because if you have 3 electrons and 3 holes in your lattice, then you create something that can conduct the conduction inside your material. And then, for instance, your insulator becomes conducting for a short while. Okay, so if we look at this curve, you can see the ion, the number of electron hole pair created as a function of the distance. This is in the air. And don't be surprised to see that. It means that the particle arrives this way, slows down, and as it slows down, it deposits more and more energy, and then it slows down again in a stronger way. And finally, we arrive to what is called the Bragg peak, this maximum of ionization and energy deposition, and then the particle stops. And this is very useful because you can predict exactly how far the particle is going and where it will stop. It's very useful, for instance, in radiotherapy, if you want to hit a tumorous zone area without hitting the same tissues on the other side. The particle will deposit most of the energy inside the tumor. It's also very interesting for microelectronics when you want to implant ions, boron, for instance, as dopants, somewhere very precisely in the semiconductor. If you do this, you know exactly at which depth you will stop the particle. So this is probably the most important chart that you have to remember in this lecture, because it's the guideline to all the effects that you may encounter. 1 gray, which is 1 joule per kilogram, creates 10 to the 15 electron hole pairs per centimeter square in silicon, and roughly the same in silicon dioxide. So this is something that you should keep in mind, because if you compare this 10 to the 15, for instance, to the number of electron hole pair pre-existing in a metal, then you see that this is negligible. So basically, radiation will do absolutely no harm to metal, okay? Because there are already a lot of electron hole pairs. The metal is a good conductor. You add just a little bit and it goes completely unseen. It's negligible. On the other hand, if you deposit those 10 to the 15 electron per centimeter square in an insulator here, you get a tremendous effect, because before there was none. So you see it, and most of the time, those electron hole pair will stay trapped. They will stay because they cannot drift or move inside the oxide or the insulator. So they stay trapped inside. And what do? They create an electric field, because if you inject charges inside your insulator, then you have what is called an electret, and then you create an electric field in this. And in between, you have a semiconductor, which has a density of carrier between 10 to the 12 and 10 to the 19th. So in this case, if you deposit 10 to the 15th, you will have a transitory effect. You will see it on the moment, but very swiftly, those electron hole pair will recombine because they are in the middle of other electron hole pairs, and the semiconductor will come back to steady state, to the normal. So remember, radiation will affect a lot insulator, will have no impact on metal, and have a transitory effect on semiconductors. If you know this, you can use your brain and think about what kind of effect you will have on any device. So I would like to introduce you to the basic mechanisms of radiation effects in electronic device. And this mostly happens on what is called the SiO2-Si system. Typically, you have a bulk of silicon right here, and it's covered with a layer of SiO2. And this SiO2 has traps, pre-existing traps inside the oxide. And when the radiation creates electron hole traps, the holes, the traps will be charged positively in there. And then what happens is that if you have a positive charge in the oxide, it will act as a capacitor. So you will create a negative charge at the interface. And if you, in the case of a MOSFET device, for instance, this charge at the interface will make possible for the current to flow in the device when it should be off. So you will turn a transistor that was off into a transistor that is on gradually. So you create a leak. And if you model a very simple equation of the drain current in a MOSFET as a function of the gate voltage and the threshold voltage, you see that this oxide trap charge impacts on the threshold voltage, reducing the threshold voltage, and then the curve shifts toward the left on an NMOS device. So it means that if you look carefully here, you see that, for instance, for 1 point something volts VGS, the transistor was initially off, and then we have a non-negligible current. So you create a leak. Imagine that in a microcontroller, you have 10 to the 9th, 10 to the 10th transistors. Multiply this leak by the number of transistors you have in the device, and you will see the bias current, the supply current, increase drastically on your device, on your microcontroller or on your microprocessor or in your memory. And if all the devices in your spacecraft see their supply current increase, then your power supply system will not withstand it. So it goes from physics to system problem. So it's something that you have to take into account. There's another problem, which is the creation of what is called interface states. Basically, it's the depassivation of the links between silicon and the pending liaison between the silicon and the oxide. And those will act like traps. So if you've got a poor carrier coming this way, it will be trap, detrap, trap, detrap. And this will affect the mobility of the carriers. And in this case, if you affect in the same model, if you change the mobility, you reduce the mobility, you see that the curves becomes flatter and flatter. It's the slope that is changing. It's not a shift. If you make a quick calculation, I'm not going to spend much time on it, but you can do it. You can just remember that, for instance, if you take a power MOSFET with a gate oxide of 50 nanometers, the shift induced by 1 gray on this transistor on the threshold voltage is about 0.9 volts. I would say, let's remember 1 volt per gray. So it's critical because your device may get doses like 10 kilowatts, so tens of grays in flight. So basically, if you have a switching power supply, and then your MOSFET starts to leak, then you put a short circuit in your EPS system, and then everything blows up. So radiation should be a big problem in there. If we look at the advanced CMOS technology, as you may know, the oxide thickness is reduced down to a few nanometers. So there's not much space to trap charge, and even if charge was trapped in there, it would be annealed very quickly. So what happens is the gate oxide is almost immune to radiation effects. However, between the cells, you may have a thick layer of field oxide separating the CMOS cells or the transistors. And if you trap positive charge in this field, then you get a negative charge image here. And then you create a channel between the two different cells, and you create a leakage in the device. And this leakage, once again, will increase the supply current of the device, creating a leak. So this one is for you, Victoria. This is the results that we had on a bipolar junction transistor. And this is actually the payload that we were supposed to fly on Baumanets. As you can see, we flew it from July 2017. It's still working. It's still providing results every day to us. And you can see the drift of the input bias current of the op amp over the months, increasing and increasing. And guess what happened here? You remember what I said earlier? We had a huge solar storm in September 2017, and it created this immediate damage on the device. And then we had a few minor solar storms. So this curve basically scales perfectly with the activity of the sun. And you see that the input bias current has increased significantly. Although we are in low orbit, 500 kilometers, and we are at the minimum of solar activity. So guess what it would have been if we had been in maximum of solar activity and in higher orbit. So it's not negligible. Okay, give you a summary of total ionizing dose on electrical parts. So the charge trapping in the oxide creates parasitic fields, electric fields. Interface traps degrade the mobility. They increase the recombination of minority carriers. Sorry. The impact of most devices is the shift of the threshold voltage. You also have a leak between CMOS cells in the field oxides. And the main impact of BGTs is a reduced current gain. Current gain could be divided by a factor of 100 very quickly. Just a word that is also useful about the displacement damage dose. So displacement damage dose is caused by a particle flowing through the lattice and interacting not only with electrons, but with nucleus. And basically what it does is that it will sweep the nucleus out of their sites. They might rearrange with dopants, usually, but they create what is called a Frankel pair, which is a hole basically in the lattice and a dopant that is not where it should be. That's a Frankel pair. And this, the primary knock atom, the atom that was its first hit, takes a significant kinetic energy. It will hit other atoms and will create clusters like this. And if you have a look at this graph, this figure here, you remember the picture of South Africa that I showed you. And it was exactly that we got. Several interactions caused by several nuclear reactions inside the lattice. And basically what it's doing is it's turning your silicon into Swiss cheese in the end. And what does it do practically? Practically, it's if you look, for instance, at a CMOS imager, you take a picture in the dark. You should have only a black square on the picture. But after irradiation to protons, what you get is a lot of dots, and those are permanent dots. Okay, they are permanent damage, and all those dots will completely mess up your picture. It's not useful anymore. And as you can see, how do we know it's displacement damage? Because if you irradiate with cobalt-60, with gamma rays, which create only those TID, then you don't see this. The picture remains black. So remember, protons will impact optoelectronic devices, photonic device, and will have an increase of all the leakage currents in the diodes, for instance. Another famous...
Mr. Dussault, I'm sorry. Could you please maybe speed up, because we have another lecture at 7. Thank you.
Okay, I would just like to finish with the single event upsets. They are much more known, and mitigation effects are more at system level. So I didn't spend too much time on that. But you know about the single event upsets on SRAM, for instance, which is the the information on a couple of inverters being latched by when a particle goes through in the RAMs. But remember also about these MCUs that I was mentioning earlier. And because this you cannot mitigate with system and software techniques. C5, I will just stop your microcontroller. And I would like to have introduce you to the killer, the latch-up. The latch-up is caused by this structure. It's a thyristor structure in which if you trigger, for instance, this junction, you have a current passing through. It triggers this junction, and then you have a current passing through, and then it's a vicious cycle. And then nothing limits the current anymore, and your system blows up. So it's a really bad killer, and it's causing a lot of death. So what are the mitigation strategy? For the SOUs, you choose parts carefully, evaluate the cross sections, evaluate the risks, implement error correction, triplicate, use odd redundancy. Don't forget watchdogs, automatic reset when it's possible. Then for destructive effect, it's useful to use derating, which means that you use, for instance, if your MOSFETs can break 100 volts using at 40 volts, it's very useful. And my recommendation is for a moon mission, never use COTS parts when human safety is at stake. Always don't take the risk, always use radar parts. Summary is basically what I just told you, so I'm going to skip it. The references that I have used to prepare these classes, and my acknowledgements to a few senior experts that gave me some materials, and Final Information, and the REDEX Association members. Q&A if needed. Any question?
I have a quick one, if we have time.
Yes, please go ahead.
Why are we not able to create an artificial EM field to protect ourselves just like the Earth has?
Make a quick calculation. This is a good idea. It's a very good idea. It's being investigated. The question is, how much energy do you need to create this field? If you run an Elmos coil, for instance, and you want to create one Gauss in, let's say, 1 meter square coil, you need 4 amps, roughly, if I'm correct. I remember. When you're on a spacecraft, where do you get this energy from? So the idea is really good, and it will be the best thing to do once we know how to produce this energy. Until then,
would not like a nuclear reactor or something that if we figured out how to get one to be able to be built like on the moon work, wouldn't that produce enough power?
Sure, if we have the ability to carry a nuclear plant on the moon, then we have plenty of energy. But that doesn't solve the problem of getting there, first. And second, producing the magnetic field, yes, it requires a lot of energy, but it raises also other questions, such as nuclear safety on the moon, if you have a nuclear reactor. How do you cool it, for instance? How do you cool your reactor? How do you get rid of the neutrons? You may create more problems with a nuclear reactor on the moon. And if you want to use a thermonuclear, just like on the Martian rovers, for instance, it's not very efficient. The efficiency is not really good.
Okay, thank you.
You're welcome.
I wanted to ask if I understood correctly, you mentioned at the beginning of the presentation that I guess like light molecular weight organic compounds are good good radiation shield. So does that include things like composite materials, like epoxy and polymer-based materials?
First, let me remind that this is only valid for neutrons, okay, for energetic neutrons, because you want to degrade their energy. So every light material that has compounds, yes, basically, if the mass is close to the hydrogen mass, will be good to thermalize neutrons. But you have to be careful not to include nucleus that can be activated by the neutrons and create back reactions. So it's, as I said, it's a tricky thing, and it has to be calculated with using giant 4. You know, for instance, in the ITER fusion reactor, it's a problem how to get rid of those neutrons.
Okay, thank you. If I could ask just one follow-on question. So I guess I also wanted to ask, like thermal shielding, like the ablative composites or like the ceramic tiles used on the space shuttle, as they're both good insulators, would they provide any like measurable radiation shielding?
They would definitely help shielding against protons and electrons. I'm not sure how good they are for neutrons. But you don't have neutrons in space. I mean, it's only at the moon surface or under the regolith. But they will definitely shield you, yeah.
Okay, thank you.
Do you have any idea of the density of those materials? I'm not an expert in this.
Oh, the ablatives are usually about, I think, like 1 to 2 grams per centimeter cube, but the ceramic tiles are very low density, like less than 1.
It's if you want to try the calculation, just use the star P star, create your material with, you can create your own material. It's very easy to use. And then you make your calculation, and it gives you the curve at once. A giant 4 is very difficult, but star P star, it's 1 minute to get the answer. I invite you to do it.
Okay, thanks for your answer.
You're welcome.
I had a question. I noticed the Apollo 14 radiation numbers were higher than the others. Why is that?
If I correctly remember, it's because they spent more time on the moon. The radiation figures that I gave were oh yes, that's true. They probably experienced some solar event or something at that period. Yes, you're right, you're correct. I thought it was Apollo 15. There must be something wrong. I'm just wondering if they didn't exchange the values, but the only explanation that I can see here is that they had some solar events during the moonwalk.
What about well, dosimeters? Because maybe it's because of some of dosimeters was wrong. Because at Apollo 17 mission report, there was some details about that dosimeters was show the wrong numbers. Well, maybe that's the reason, but I am not sure.
I've heard about that for Apollo 17, but I have not heard about that for 14. It should be investigated. I don't know. I just don't know.
Okay, thank you.
You're welcome.
Varan, It's Vladimir Igritsky. You know, in our project, students have huge hydrogen tanks on board of their spacecraft. So can we use some kind of superconductivity to make magnetic field without nuclear reactor? Because if we have superconductor, we can use magnetic field without any additional current, I think.
Yes, definitely. If you have a source, if you can produce enough energy or use superconductivity to create a magnetic field, it's a good way to shield yourself. Yeah, on the moon surface. Yes.
Thank you very much.
You're welcome.
Can I have a questions? My name is Baujo from Bauman University. For your opinion, what's the most well dangerous particles or rays when we will flight from the Earth to the moon, from Earth to the moon?
On the way, during the way.
Yeah, during the way. Yes, yes.
It's definitely the protons, because the electrons, there are a lot of electrons, but a lot of them have low energies and they will be easily stopped. The protons, some have significant energies and will be difficult to stop, and they will deposit a lot of energy in your devices, and so I would fear the solar protons on the way.
Solar protons, you said?
Yes.
Okay.
Solar protons from solar events.
So if there is no solar events, so the dangerous particles will be from the galactic rays.
Yes, but the particles from the galactic rays, they have a very, very high energy, so you cannot shield them, but there are not so many. So in terms of total ionizing dose, and it's less than the solar wind or solar protons.
So
what I would fear is that you have a heavy ion, very heavy ion like iron, for instance, with a high energy from a galactic ray coming and creating single events in your microcontroller, for instance, or in your memory. In this case, you will have a tremendous effect, but there's nothing you can do about it. It's just too energetic to shield it.
Well, I know that there is some technologies that they have very thick layers that can protect the devices or CMOS. Yes, I think so. Can we use this thickness layer in the inner part of our capsules with the crew members?
It's a question of trade-off. You can do anything, but the question is, at system level, can you afford it? If you put the significant amount of shielding and the right material, you can always do it. I mean, if you've ever been to CERN in Geneva, they have the 24 JeV per C protons beam that is injecting the protons in the LHC, okay? And they stop them, but it takes 25 meters of concrete.
Okay.
See what I mean? Can you afford to have 25 meters of concrete on board your spacecraft?
Okay, I get it.
You see, it's system level. What's the risk? Can you accept the risk? Can you mitigate the risk?
Okay, thank you.
That would be a second lecture, I say, because it's a lecture that I cannot give without introducing all the material I gave today. But it's just becoming interesting now.
So will you share with us your contacts so maybe we can make some kind of these lectures in the nearest future, I think.
Sure, of course. Who shall I send the slides to?
The email I wrote you about the lectures.
Okay.
And Mr. Dussault, thank you very much for your presentation, for your very interesting knowledge you share with us. Unfortunately, our time is out for this one. We hope we will manage to make another lecture, but not today, as we have another lecture in 20 minutes.
It's fine, it's okay.
Спасибо большое, дорогой профессор. Мы надеемся на дальнейшее сотрудничество, на интересные проекты, на интересные идеи.
Thank you very much, dear Laurent.
Thanks for inviting me. It was a pleasure.
And we are looking forward for the future cooperation, interesting projects, interesting ideas.
Спасибо и до новых встреч. Надеемся на очную встречу. И в следующем году наша школа обязательно будет. И мы приглашаем вас приехать лично и прочитать, глядя на ребят.
And we invite you to come for the next summer space school and give a lecture live, face to face.
Thank you.
Всего хорошего.
Спасибо.
Thank you so much.
Thank you.
It was my pleasure to participate in this and give this lecture. Don't hesitate to candidate if some students want to come to Montpellier, they are welcome, okay, from Bauman or anywhere else. And we really hope to be able to collaborate again on a space mission with you, Victoria, as soon as possible.
Вот, получил удовольствие от этой лекции. Спасибо большое за приглашение. Если у кого-то из студентов есть интерес, всегда добро пожаловать в Монпелье. И с вами, Виктория Ивановна, с радостью буду взаимодействовать и сотрудничать по новым космическим экспериментам.
Thank you. We have ideas, new ideas. Thank you so much. Bye-bye.
Bye-bye.